be 130. So this is where we left off talking about the about thermodynamics, and first law is conservation of energy. Change of internal energy of system is the work plus the heat, and then we define the system. And energy flow into the system is positive, energy flow out of the system is negative. And then we talked about heat transfer, and there's a lot more about heat transfer. So this is a really abbreviated portion of it, especially if you go into mechanical engineering. There's a lot of stuff on heat transfer. And some simple heat transfer. I mean, there's other types of heat transfer, but for this class, to be real simple, heat transfer is the heat capacity times a change in temperature. We can describe the heat capacity as if it's a single substance, the mass times the specific heat capacity. The specific heat capacity is akin to something like density, where it's an intrinsic variable. So, and now we're going to go over another example. And in this example, you have a water bath you submerge a 32.5 gram cube of aluminum that's initially at 45.8 degrees Celsius into 105.3 grams of water at 15.4 degrees. What's the final temperature of both substances? So let's think about this for a bit. You have water at 15 degrees, and you have aluminum at 45 degrees. Aluminum, and I already looked this up, well, it's in the textbook, not like it took a lot to look up. Water's heat capacity, which actually I do memorize, 4.18 joules per gram degree Celsius. And then heat capacity for aluminum is 0.9 joules per gram degree Celsius. So let's think about the answer before we start. You have about 3 times as much water, and the heat capacity is more than 4 times. So in my mind, I'm thinking, okay, the water is going to go up a little bit, and the aluminum is going to go way down. So that's kind of like my check, as I keep on going. And for me, myself, I always think about the heat transfer because of the dreaded negative sign. It's always, I've done that thing where I missed the negative sign in one of my calculations, and I just had to do it once. And I am always super careful about the energy direction, the flow of energy. And I even drew it here. You have the aluminum block, and the heat is going out of the aluminum. So, the book does it a little differently. The way the book does it, it says that the heat transfer is just opposite of each other. I always think that the direction, and I do it in the intuitive right brain approach. I always think about where the heat flow is going rather than the equations. So, although here I am about to use an equation. So in my mind, I'm thinking the heat transfer of the aluminum is negative, and it's going to equal the heat transfer of the water, because I'm using W, not H2O for water, because H2O is just 3 things to write. So so heat transfer is negative there. The book has it differently. They put the negative on the water for some reason, but we're going to do the Mike Ferguson method this time around. So and this is where I'm starting off with the equations. And the reason why I'm starting off here, like I said, the heat transfer, and so remember, energy is not created or destroyed. Any heat that leaves the aluminum is going to be absorbed by the water. And also it says, assume the aluminum water are I'm talking to my iPad, sorry. Assume the aluminum and water are thermally isolated from everything else. That means that there's no heat loss or heat coming in from outside sources. So all the heat there is confined to the water in the aluminum system. So does everyone get that, where I'm coming with this? Okay. So now let me write another equation, and I'm gonna drop aluminum to just A. So the heat of aluminum, so we're gonna have minus the mass of aluminum, the specific heat of aluminum, and the delta T of aluminum equals the mass of water, specific heat of water, delta T of water. So you okay with that? Okay. And delta T is always final minus initial. So delta is always finest minus initial. So minus M aluminum, CS aluminum, TF minus TI. Actually, I don't have to do the aluminum for the TF is just the same for both. Equals mass water, CS water, TF minus TI water. So, okay, everyone good? So, okay, I'll just keep on going. The book starts putting in numbers. So I myself, I like to do all the algebra. So for the other mistake I make is I still make this mistake. I put my numbers in the calculator wrong. So that's my other very common mistake. And so I like to do all the math first, at least all the algebra first, and then I do the inputting the numbers once. So that way, if I screw up, I can go back. And that's when I also said, like, hey, I'm looking for a number that's a little bit higher than, so it's the water's at 15.4. I'm looking for a number around 20-ish degrees. You know, in my mind, I think that the answer is going to be 20 degrees. So if I get something completely wrong, I know I did something incorrect, and I'll probably look at the calculator. Okay, so then next thing I do is FOIL it. So minus MACSATF plus, I'm just, you know, multiplying, you know, so I guess it's a cumulative, is that what it is? I don't know. I guess foiling is something different. I don't know. Who are the math folks here? MACSATIA equals mass water, CS water, TF minus mass water, CS water, TI water. And this is where it's nice when you have an iPad, because then you can start moving things around. So I'm just going to take this and copy it, paste, and I'm going to move this over here. So I'm just adding it to this side, adding that to that side, with a plus sign there. And so I just moved all the TFs on one side. So now I'm going to take the TF out. Mass of water, CS water, plus mass of aluminum, CS aluminum. So, and then my last step, I'm going to divide. So I'm going to copy this. Copy, paste. Divide. So rather than write everything out, it's, like I said, it's kind of fun to have an iPad. Cuts the writing time down. So if you look at the top equation, well, the top equation, this is, well, maybe I'll go back. I did the cumulative operation. Now I have this, and I'm going to put the TFs on the right side. So I added the negative mass aluminum, CS specific heat of aluminum, specific heat capacity of aluminum, final temperature on the right side, and then the other one, the negative mass of water on the far right in the top, specific heat of water to initial of water. I moved it on the left side. And so then we have the second equation on the page, and the third equation, I factor out the final temperature. And the last one, I divide the terms. So then you get the final temperature. And then you just put in the numbers. And Look at the textbook. All right. Mass of water is 105.3 grams. Heat capacity of water 4.18 joules per gram degree Celsius, plus mass of aluminum 30. Oh, I forgot the initial temperature. Huh. I'm already making mistakes. Okay, and initial of water is 15.4 degrees Celsius, plus mass of aluminum is 32.5 grams. Heat capacity 0.903 joules per gram degree Celsius times the initial. Where's the initial? 45. Okay, yeah. Thank you for the assist. Mass of water, specific mass of water, 105.3 grams times 4.18 joules per gram degree Celsius, plus 32.5 grams times 0.903 joules per gram degree Celsius equals final temperature. You put that all on your calculator and you get 17.3 degrees Celsius is the final temperature. And I can't really show you how I put the numbers in the calculator, so I'm not going to, unless do you want me to put the numbers in the calculator just to make sure that I did all my algebra right? I'm pretty sure I did. But does anybody have any questions so far? Oh, you're gonna put the numbers in the calculator. Oh, that's a good idea. Class activity, I like it. All right, I'll join you. All right, my free calculator app, which will. Okay, 105.3. Yep. I got 17.3. Ooh, and I got an ad on the US border crisis. All right. The only ads that I get that really make me angry are the ones for hair products. I'm just like, that's just rude. What, you're sorry that you're laughing at my jokes?
I'm sorry that you have to deal with that.
Crippling case of alopecia, huh? Okay. So yeah, so I've gone ahead and verified that. The book goes through a different, you can input the numbers anytime when you do these. I mean, the algebra is the same. I just like to do the algebra first. That's just my own personal preference. You're welcome to put the numbers in as you go, by all means. So however you do it, it's fine. Okay, so recap for this problem. We have a water bath at 15.4 degrees, and we throw in a hot piece of aluminum. And we want to know what the thermal equilibrium is. So we let it sit for a bit, and we want to know what the final temperature is going to be. And so we can calculate that out. And the idea here, I mean, so there's no heat transfer other than between the aluminum and the water. Of course, in the real world, there's going to be heat transfer, right? But we're hoping that this is fast enough that there won't be significant heat transfer, or it's very thermally isolated. So I mean, and the heat flow from the aluminum is negative, so it's going out of the aluminum, it's going in positively into the water, and which we can then say that the heat transfer of the aluminum is the mass of the aluminum, specific heat of the aluminum, change in temperature of the aluminum. Same thing with the water, mass water, heat capacity of water. So I should say specific heat capacity of the water, and the change in temperature for the water. Delta T is final minus initial. We write it out, do the algebra, and then plug in the numbers and then get it correct, plus some weird adds if you have a free cell phone app like me. So questions of how to do this? Yeah.
I have a question as to why the book put a negative on the water and a positive on the.
So they're just saying that the heat transfer in one direction is opposite the other. I wondered about that myself. I don't know why let me see if they say that. Where does the book say that? It just says conceptual plan. The heat.
To do with the system?
No, because the system would make the aluminum be negative and the water positive. I mean, that's universal. Out is the negative direction, in is the positive. Is this in the book? It says strategize the heat loss by the aluminum equals the heat gain by the water, and they just go from that. So I mean, it's correct. I mean, the math would work exactly the same because you just put the negative on the other side. So I don't want to do it again though. I could. I mean, algebra is easy, but it's also kind of a pain. Other questions? Okay. All right. Pressure volume work. So to inflate it, well, this is I'm just giving you the equation. One of the equations is work equals minus P, the pressure, times the change in volume. So that's one of the definitions of work, at least for an expanding gas, right? So, and if you like, I don't know, you ever buy one of those floaties and take it to the beach and then you want to float in it, so you sit there on the beach and you blow it up, and after like 5 minutes you're lightheaded, and because I mean, it's also, you're doing work, right? It takes work to blow that thing up. And if you wonder how much work you're doing on the thing, you could do it by minus pressure change in volume. So, and here the external pressure would be 1 atmosphere. And then the change in volume is however much you blow it up. So instead of one of those floaties, instead we're going to inflate a balloon from a volume of 0.1 liters to 1.85 liters against an external pressure of 1 atmosphere. How much work is done? So, and as you know, it is work blowing up those floaties. So use the work minus P delta V, and you're like, okay, so your work is going to be minus 1 ATM. Change of volume, so delta is final minus initial, 1.85 minus 0.1 liters. So this equals minus 1.75 liter atmosphere. And what the heck is a liter atmosphere? So what you can do, and I know it's 101.3. So I kind of have it memorized, but a way you can get that, or the way that you get that though, is a joule. So if you do the 8.314 joule per mole Kelvin, that's one value of R, 0.08206 liter atmosphere mole Kelvin. You can see that if you divide these two, the moles Kelvin cancel, and you get 101.3 joules per mole. Oh, sorry, joules per liter atmosphere. So I think it's 101.3. I hope I'm not going to embarrass myself.
Is it a kilopascal?
No, kilopascal is 1,000. That's 100. So then the way you can convert this, minus 1.75 liter atmospheres times 101.3 joules per liter atmosphere, and liter atmospheres cancel, and you get minus 177 joules. So I always had truth be told, I always had a little bit of a hard time with this one because it also depends on how you define the system. So in this case, you're doing work on the surrounding. As the balloon is expanding, it's pushing on the surrounding. So that's where the negative direction is. So, right, so you're blowing up, you're blowing it up, and so that means the work is pushing out, and that's why it's the negative direction. I'm trying to push, I'm doing this way because, you know, it's a gas and it's expanding, it's pushing in all directions. So it pushes out from the surroundings, if you're wondering with the directions of that. And then, you know, likewise, if you let a balloon go, it flies around kind of thing. It depends on your system, I guess. Then, I mean, that would kind of also be in the negative direction because it's thrusting outwards. So it's kind of, to me, in my mind, it's kind of weird that you would have negative work when you're blowing up a balloon, and then when you let it thrust away, it's negative again. But I mean, I guess you're just defining your system. If your system is the surroundings, so it's going to be negative when you inflate the balloon, and then the idea is the system does work on the balloon as it's deflating. So then that's the positive direction. So it's kind of like whatever you define your system. So and it's kind of contextual as well, like I said, because you can have the balloon saying it's a thrust and it's going out. That's another way of saying it. But the negative sign is inconsequential. It's just when you have two things, like when you're equating energy flow in one direction to the other, one of them has to be negative. So, but how can you answer the questions? All right. Now, am I the only one that reads like nutritional information like very carefully? Like, okay, you guys do it too. Or you don't, or you, okay, you do or you don't? I'm curious.
I do.
You do, okay. And especially like the ones that now that we're getting all the new sweeteners, artificial sweeteners, like the whatever it's like, the stevia, and I guess, has neotame hit the market yet? I guess no. I know sucralose. I don't like sucralose myself, but you'll see these things like a Diet Coke or something like that has 4 calories or something. Like how do we figure that out? You know, how do we figure out the number of calories in these things? And the answer is we use a bomb calorimeter. Do I have a picture of one? No, I don't. I should have put a picture of a bomb calorimeter. Here, I'll take a picture of it. All right, here is a bomb calorimeter. So, and they're huge, by the way. The ones that I've used, they're about this big and about this tall, and they're really thick. So, and then they have, like, you can see the picture of the leads on there. I mean, this is something, it's not gonna be easy to move. And what you use the bomb calorimeter for is that you burn stuff in it. Okay, so you burn things, and the idea, so remember that internal energy change is path independent. So the idea is if you take Diet Coke and you put it in one of these bomb calorimeters, well, you probably dehydrate it first, but so you put the dehydrated Diet Coke in there, and you burn it in the bomb calorimeter. The idea is that if we burn it in here, that's the same as if our cells, went and burned it inside of our mitochondria. So, but at the same time, can we really get energy from sucralose or something? I don't know the answer to that, to be quite honest with you. I always kind of wondered about that. Like, sucralose is Splenda. Like, can I actually get energy from Splenda or stevia? It's probably more likely that I get it from stevia from Splenda. So, and like I said, the change of internal energy, it's path independent, and so we use the bomb calorimeters for stuff like the calories in food. Okay, so the bomb calorimeter, 1.01 grams of sucrose, that's table sugar, undergoes combustion of bomb calorimeter. The temperature rises from 24.92 to 28.33. Find the change of internal energy for the reaction of combustion of sucrose in kilojoules per mole. The heat capacity determined in a separate experiment is 4.9 kilojoules per degree Celsius. Okay, so the idea here, so the delta E is going to be, so minus Q. And again, it's the chemical, like what you define as a system. For me, I'm going to define the system as a chemical reaction. And actually, I already know that it's negative because the heat goes up. You go from 25 degrees to 28 degrees. So temperature goes up, which means the heat flow into the bomb calorimeter to the calorimeter, it's the positive, that's the delta positive Q. And then the heat going from the chemical reaction is a negative direction. It's losing energy. So it's losing internal energy, losing, and the heat, that's why I have the heat is a negative sign. So, okay. And like I said, I always, because of that dreaded negative sign, I always think where the heat flow is going, so I don't ever make that mistake again. And this time though, the heat, we usually use Q as MCS delta T. So instead of this equation, we're going to use just C for the heat capacity. So that's the heat capacity. So we're not doing the specific heat capacity that was already found for us. So the heat capacity is 4.9 kilojoules per degree Celsius, and the delta T is final minus initial 28.33 minus 24.92 degrees Celsius. And so the change of internal energy is going to be, or minus Q is going to be 16.7 kilojoules. So, okay. So it's giving off 16.7 kilojoules. And so, and remember, this is per 1.01 grams of sucrose. So we need to figure this out by the ratio. So this is, so we have, I'm going to go ahead and put the negative sign here, negative 16.7 kilojoules. Then we're going to divide by 1.01 grams sucrose times the molecular weight of sucrose. Sucrose is, oh, it's already up there. It's here. This is 342, 342, I don't have the 42.3 grams per mole. So times mole sucrose pour 342.3 grams sucrose. So I'm dividing this because of the units. So, and as you divide this out, you get minus 5,660 kilojoules per mole. So, yeah. Find, why am I doing all that? So if you see here, it says find delta E in kilojoules per mole. So what you've done is you figured out that it releases 16.7 kilojoules per 1.01 grams. And then, so this tells you the ratio here between this much. So you divide this by the grams, but then convert the units on the bottom with the grams to the moles to get the proper units, what it's asking for, the kilojoules per mole. So if you think of something else, like if I wanted to figure out the cost of, I don't know, flour. I mean, I know when you go to the store, you can buy flour. It tells you the price. Let's say, your friend comes, I bought this baggie of flour for 50 cents. What is the price per pound of this bag of flour then? So how would you figure that out? Well, you would take the flour, you'd weigh it, and let's say that it was 1/10 of a pound, right? So if this bag of flour, okay, use my cell phone, this bag of flour, I weigh it, it's 1/10 of a pound, and it was 50 cents. So then 50 cents divided by 0.1 pounds would then be $5 a pound, right? So if I want to know the price of the flour, that's how I would figure it out. Same idea, instead of money, we're doing energy. So we burn 1.01 grams of sucrose, and we get 16.7 kilojoules of heat from that. So how much energy then does sucrose put out per mole? And just like the flour, like you divide by the unit to get that. But I mean, the other difference is there's conversion, because 1.01 grams of sucrose is going to be about 3 millimoles, so about 0.003 moles of sucrose. So you take the energy, divide by the moles of sucrose, and then you get the energy per mole. And again, I always think back to the direction of flow. So heat flow is negative, the temperature is going up in the bomb calorimeter, which means the reaction is putting out energy in the negative direction. So this is all correct. So I'm getting some confused looks on your faces. I need to let it sink in. Do I need to do interpretive dance? Energy out, negative direction, divide by units. Dimensional analysis, answer. What's that? Oh, yeah. The questioning. Are you questioning my sanity? Oh, we got a chat. What does the chat say? Is that dance real? Yes, Eli, it is real. That's my PhD is in chemistry, not in interpretive dance, unfortunately. Yeah, they can. Oh. At least they can see me up to my face mask. Okay. They can see from about here to here. That's what you're missing, Zoomers. Okay. Do you want me to explain it again? Are you guys? Is it? Do you need some more sinking into it, or do you want me to explain it again? I'm trying to. No, you got it? Okay. All right. I'm just trying to read your faces, and there's just some of those. What the heck? Does it make sense with the flower metaphor? Not really? Okay. Yes. Okay. All right. So here is your chest. 18 grams of glucose. Burns in a bomb calorimeter. 1 kilogram. So, although this time I didn't give you it's 1 kilogram of water, raises from 10 degrees Celsius to 7 degrees Celsius. Specific heat capacity of water is 4.18 joules per gram degree Celsius. What is delta E reaction for the oxidation of glucose? So I'll give you a couple hints. 18 grams of glucose. Glucose is 180 grams per mole. So this is 0.1 moles. And then if you want to do the heat capacity, it's going to be mass times CS, which is going to be 4.18 kilojoules per gram degree Celsius.
It's the same as water.
It's a kilogram. So 1,000.
Oh, joules.
Yeah. Oh, it's not going to be grams. I'm sorry. It's just going to be kilojoules per degree Celsius.
Okay.
You're right. Eli wants to know if the dance is going to be on the test. Oh, God. Eli, as much as I'd like to put that on a test, it's not in the student learning outcomes. Although I guess I could change it. That whenever we do something like that, we have to go through curriculum committee. I'd love to see that. Like, what is the purpose of students must do interpretive dances for thermodynamics? Is anyone here completely stuck, has no idea what the heck's going on? Good. All right, cool.
How do you have this listed positive and negative?
Well, I was doing like the book for this one. Heat flow of the chemical reaction is giving the negative direction because the bomb calorimeter is increasing energy. So the heat flow into the bomb calorimeter is positive. The heat flow for the chemical reaction is negative. Right, so it's giving off energy. So, and I'm making sure that there's negative, but you can also think of it that way. Just make sure there's a negative at the end. So, and this is something you can kind of do. I mean, with a multiple choice question like this, I would look at 60 times 4.18. I would guesstimate that 60 times 4. That's about 240. Divided by 0.1, that's going to be 2,400. Negative sign, negative 2,400. A is the only answer that kind of makes sense then. So that's something called an order of magnitude calculation. Right there. I know I didn't even ask people to vote. But I mean, that's something you can just kind of divine out. The other thing is, since the temperature goes up, you know that B and D are wrong. So it's either going to be A or C. So those are the only ones that are negative. So, but then you just have to do the math. But questions with this one? Were you guys actually asked? Would you guys get A? Was that okay? I should have asked you to vote. That's good. It's so it's making sense then. All right, so I know I said that I was not a master artist, but you will see my extra art ability. So exoskeletons, right? So insects have exoskeletons. So that means that they have their skeletons on the outside. A lot of other arthropods too, you know, like crabs and lobsters. So I guess other arthropods like centipedes and millipedes. I guess those aren't technically insects because insects have 6 legs, right? I'm not very good at biology. So the arthropods, they have exoskeletons. We humans, we have endoskeletons. We have our skeleton on the inside, right? So look at the word exothermic. Exothermic, so that's a flame. That's you know, you have a burning flame and the heat is leaving the system. And you go and you put your hands by a fire and you can feel the heat. And that's the negative direction. So exo, like an exoskeleton is on the outside. So exothermic means thermo leaving, thermic, heat leaving is exothermic. And endothermic, so endo means inside and thermic, so heat going on the inside. That's the energy in the positive direction. So that's my snowman. You know, so snowman, and I just think, I know it doesn't snow here. Well, I guess it doesn't snow very frequently here, and not at this altitude, but energy, well, you know, snow in my mind, I consider it to be cold. So that's why I think of, you know, energy going into the system. So endothermic. So endo, inside, thermic, you know, heat energy. So inside heat energy, endothermic. So makes sense. And next thing we're going to talk about is enthalpy. So enthalpy, we give it the term H. And we define enthalpy as the internal energy plus pressure times the volume. And then if you, well, how many of you guys are in calculus? Do you do the, have you done the product of the product rule for derivatives yet? Well, if this is calculus here. If you take the derivative, and now calculus is not a prereq to this class. If it doesn't make any sense, then go about your day and don't worry about it. The derivative of pressure times volume is equals to the derivative of pressure times the volume plus the derivative of the volume times the pressure. So the idea, though, is if the pressure is constant, then this term goes away, and the derivative, and you're left with the what? Well, the change, the change in P. Yeah. So the P prime, the derivative pressure would be 0. So 0 times anything other than 0 infinity, but is 0. So then that term goes away, and you're left with the derivative of pressure time, and I'm sorry, derivative of volume times the pressure. So taking the change in enthalpy, you get rid of the change in pressure term, and you get the change in enthalpy is the change in internal energy plus the pressure times change in volume. And also, you can take this further. With the first law here, the change in internal energy is work plus heat. And P delta V, that's negative work. So if you plug that back in, you get the change in enthalpy is equal to the heat transfer. And so you can see then delta H is equal to the heat transfer at a constant pressure. So frequently we refer to the enthalpy as the heat of a reaction. And we do this quite a bit, especially here on Earth, because the pressure here tends to be relatively constant. So for most applications, for humans operating on Earth, enthalpy is just going to be equal to the heat flow at constant pressure. And quite frankly, I use enthalpy. Most people use enthalpy more than they use internal energy. So enthalpy is very, very commonly used instead of delta E. But another thing, so I mentioned this also a little bit last class. Internal energy is path independent. So enthalpy H is also path independent. It's an exact differential. Later on, you'll learn about Gibbs energy. That's more next semester. Gibbs energy and also entropy. These are all path independent. There's some more terms. Helmholtz free energy, that's capital A. That's also path independent. But for this series, this chemistry series, the independent variables, the path independent variables are going to be internal energy, enthalpy, Gibbs energy, and entropy. So, okay. And summarizing for enthalpy. So the value of delta H for a chemical reaction is the amount of heat absorbed or evolved in the reaction under conditions of constant pressure. And if it's positive delta H, it absorbs heat, which means it's endothermic. And negative delta H means exothermic, which means it feels hot to the touch. So certain chemical reactions and certain processes are exothermic and some are endothermic. It's easier, I think it's probably easier to think of processes. I mean, chemical reactions, well, it's easy to think of the exothermic ones because they burn and explode. Those are the negative ones. But for processes, melting of solids, that's endothermic, right? So if you hold an ice cube in your hand, it feels cold. Not just because it's, it is colder. It's going to be at 0 degrees Celsius, well, assuming it's at thermal equilibrium. But as you're holding on to an ice cube, the energy from your body is going into the ice cube, and it's breaking the bonds that form the solid. So that's the reason why ice feels cold. It's because it's your energy from your body or your hand or wherever you have is going in, it's breaking those bonds, and the energy then is in the positive direction for the ice. So that's the endothermic reaction. It feels cold. Exothermic reaction or process. Have you guys worked with sodium hydroxide lye yet in lab? Okay, it gets hot. If you ever take sodium hydroxide and throw it into water, it gets really hot. That's really exothermic. So you gotta be careful with that, because if you put too much, it can boil the water. So if I ever do that, I always use like an Erlenmeyer flask or something like that in case it starts spitting and it keeps it in there. So, all right, and are we doing some questions? No questions from Zoom. So we are in chapter 7. Okay. This is law. All right. So let's use some enthalpy terms. In a liquefied petroleum gas tank in a home barbecue contains 13.2 kilograms of propane. Calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. Okay, so this next concept here, we're combining the idea of thermodynamics with stoichiometry and reaction stoichiometry. So, and you can do this with dimensional analysis. So, and you have 13.2 kilograms of propane, C3H8. So 1,000 grams per kilogram. And then let's see here. 3 times 12. So carbon is 12. So 3 times 12 is going to be 36 plus 8. 8 times 1 for hydrogen, that's 44. Okay. Same as carbon dioxide. So mole propane to 44 grams, C3H8. So this is not surprising. We're turning 13.2 kilograms into moles. And now from this chemical reaction though, you can get, there are minus 2044 kilojoules per mole propane, C3H8. So let's say this was a 2, then you'd have a 2 there. But there is no 2 there. It's just straight like that. So do dimensional analysis. And here we go. So in doing this, you get negative 6.12 times 10 to the 5th kilojoules. So that's a lot of heat, by the way. That's a lot of heat. So, okay. So, right, so that's 10 to the 8, so it's 6 times 10 to the 8 joules. And 10 to the 8, what is, that's going to be 600 million joules. That's a lot of, 600 million is a lot of energy, right? No matter how tiny the unit, that's a lot of energy. But anyways, going back to this, we are doing a dimensional analysis. We start with mass of propane, convert to moles, and then the new step is looking at this chemical reaction. We can include, just like with the stoichiometric ratios, you can include energy in with it. And this tells you that for every 1 mole of propane, it generates negative 2044 kilojoules. For every 5 moles of oxygen, it's that way too. 3 moles of carbon dioxide and 4 moles of water gives that. And the units, it doesn't even include kilojoules per mole. The units on this is moles reaction. So, and it's the way the chemical reaction is written. So the moles, the mole reaction is implied. So if you see something like this, you have a chemical reaction, and then there's a heat written after this. This tells you that this chemical reaction is exothermic. So it means in the forward direction, it's exothermic. It also, if you go the reverse direction, we'll talk about this soon, that's endothermic. So going the other way is endothermic. It also tells you then the ratios. And this whole thing, like I said, is considered the moles reaction. So questions? And now we're just going through different types of problems. Measuring a heater reaction, a coffee cup calorimeter. And this is a commonly done chemistry lab question. So you do this experiment. So magnesium plus hydrochloric acid makes magnesium chloride and hydrogen gas. So 0.158 grams of magnesium combined with excess HCl to make 100 milliliters of solution, and the magnesium completely reacts. Temperature rises from 25.6 to 32.8. Find the heat of reaction for this chemical reaction as written. So, and use the density of HCl to be 1 gram per milliliter, and the heat of solution, the specific heat of solution to be 4.18 joules per gram degree Celsius. So that's the same as water. Okay, so this one is, this is kind of combining a bunch of different concepts. So it's combining the bomb calorimeter concept to get the energy per mole, like we did when we were burning the glucose and sucrose. And then it's combining the previous topic on the propane to convert the energy from that to then the chemical reaction. So how do we solve this one? We figure out the energy evolved from, well, I guess even before that, I always think about the direction of flow, the heat flow. So the solution goes up in temperature, which means that this is an exothermic chemical reaction, which means that delta H is going to be negative. So make sure at the end that there's a negative sign in front of the delta H. And then the heat flow, how much heat is going to go in? Well, we're going to have the 0.158 grams of magnesium causes the temperature to go up from 25.6 to 32.8. So we then figure out the heat transfer, and then, then heat divided by the number of moles of magnesium will then give us the delta H. So, okay, so let's go ahead and do this then. So then the heat is going to be mass. So 100 milliliters is 100 grams. 100 grams times, and this is going to be Q, is MCS delta T. 100 grams times 4.18 joules per gram degree Celsius. Final minus initial is delta T 32.8 minus 25.6 degrees Celsius. And what is that? The heat flow is going to be 3,000 joules. So we get 3,000 joules from that, and same as we did before, we have 3,000 joules divided by 0.158 grams of magnesium, then times mole magnesium, it's 24.5, what is it, 24.3, ooh, I was off. 24.31 grams magnesium. You get that from the periodic table. And doing this, you get 4.6 times 10 to the 5th joules per mole magnesium. Okay, so, and I mentioned before about the energy flow. Energy flow is going to be negative because it's going with the magnesium. The energy direction is negative because it's leaving the chemical reaction, it's making the water hot. So put the negative signs there, is in that direction. And what's nice is the way that this chemical reaction is written. There's a 1-to-1 ratio between the magnesium and mole reaction. So everything's 1-to-1 except for HCl. That's a 2-to-1. So the magnesium to mole reaction is 1-to-1. So then that means this delta H reaction is going to be negative 4.6 times 10 to the 5 joules per mole. It usually asks for kilojoules. which would also be minus 460 kilojoules per mole. A lot of times you see I'm looking at the answer in the book. It's presented by 4.6 times 10 to the 5. Usually it's written in kilojoules per mole. So you'll probably more likely see it like that. But okay, so recap for this one. I guess I also didn't mention this is also a limiting reagent problem, but it tells you excess HCl. So that tells you that HCl is not the limiting reagent. It's the magnesium metal is the limiting reagent. Anyways, we take 0.185 grams of magnesium. The temperature of the solution goes up from 25.6 to 32.8. And then from this, we figure out the heat transfer total was 3,000 joules. So 3,000 joules, we put a negative sign with that because we're looking at the chemical reaction. The chemical reaction is exothermic. Exothermic means negative direction. And then we divide by the number of moles of magnesium, and we get negative 460 kilojoules per mole chemical reaction for this entire thing. So, and the reason why we kept it with the magnesium is because magnesium is a one, it's implied by one. It's a one stoichiometric ratio for the entire chemical reaction. Questions with this one? No? Okay. Awesome. Okay, so things that affect, doing math with delta H. That's hard to read. Okay. If a chemical equation is multiplied by some factor, then delta H reaction is multiplied by the same factor. Makes sense, right? Because if I have a gallon of gasoline and I can go 30 miles on a gallon of gasoline, how far can I go with 2 gallons of gasoline? I can go times 2. How far can I go with a half a gallon? I can go 15, right? 30 divided by 2, right? So this makes sense. If a chemical reaction is reversed, delta H reaction changes sign, which also makes sense. So how much energy does it take to form glucose from carbon dioxide and water? It's the exact same amount that we get from burning it. So if the amount of energy that the plants and or the sun put in to make glucose is the same energy that we got when we burn it in our mitochondria. And then the last thing is called Hess's law. If a chemical reaction can be expressed by the sum of a series of steps, then delta H reaction for the overall equation, the sum of each of the heats of reaction for each step. So, for instance, if you have the overall equation, so imagine A plus 2B turns into some intermediate C, and then C decomposes into 2 product Ds. The first chemical equation is going to be H1, and the second one is enthalpy H2. If you look at a chemical reaction where it's A plus 2B makes 2D, it's just going to be the sum of the 2. So it all adds up of sorts. So questions? Okay, so let's do Hess's law as the next one. I think these are fun, actually. I think they're little puzzles. I like solving puzzles. So what's the delta H for this reaction here? So the heat of formation of propane. So actually, it's really hard to do this, to take carbon and react with hydrogen to form propane. That's not a very easy thing to do. This is one of those that's almost impossible to carry out in the laboratory. But you know what's real easy to do? Is to burn stuff. That's real easy. And so what I can do instead is I can burn propane, I can burn carbon, I can burn hydrogen. And I can take these experiments of burning stuff and I can figure this one out using Hess's law. So when I do Hess's law, what I start off with is I put all of the the products on the right and the reactants on the left. Even before that, I'm going to call this H1, H2, H3. So, and notice propane is a product here and propane is a reactant there. So I'm going to flip the first equation. 3CO2 plus 4 waters yields propane plus 5 oxygens, and I flipped it so it's minus H1. And then carbon's on the right side. H2, and hydrogen is on the right side. Okay, so next thing I'm going to do, this was rule number 1, right? So if you flip the chemical equation, you have to subtract, you have to flip the sign or whatever, you have to put the negative of the sign. So then I looked at the numbers. There's one propane here, one propane there, I'm fine. There's 3 carbons here and 1 carbon there. So I'm going to go ahead and multiply this equation by 3. And there are 4 hydrogens here and, oh, I put, it should be 2, sorry. I made a mistake, sorry, 2 hydrogens. I was jumping ahead of myself. 2 hydrogens there and 4 there, so what do I need to do? I need to multiply this whole equation by 2. So 4, 2, 4, and 2 there. And now I add them up. And when you add them up, so notice that the 4 waters cancel, the 3 CO2s cancel, and 3 plus 2 is 5 O2s, and these cancel. So I'm left with 3C plus 4 H2 makes propane. It's going to be minus H1 plus 3H2 plus 2H3. And then you just put in the numbers. So minus a minus 2043 plus 3 minus 393.5 plus 2 483.6. And where is that? This is going to be negative 105. Kilojoules. Okay, so if it makes you feel better, a lot of students have a hard time with this concept. So actually, it's kind of nice because I can start here and I can go over it again on Wednesday. So, okay. So we're doing Hess's law, and whenever I do Hess's law, I always put all of the products on the right side and the reactants on the left side. So the first equation, the propane is a product, so we have to flip this one, and the carbon is fine, hydrogen is fine. Then when I write them out, I'm keep in mind I'm strategizing to get towards the top equation. I multiply the middle equation by 3, the bottom equation by 2, and likewise I multiply the heats by 3 and 2 respectively. Minus 1 times the first one for flipping it, and I add everything up. I get rid of all the intermediates, and I get the original equation that I wanted, and then I put in the heat values and get the answer. So a couple of things with this one. When you do this by yourself, so if you are tasked, if for some reason you are tasked to do this, you have to find these equations yourself. And you have to come up with a strategy to find these equations yourself. There's a saying that goes, a day in the library will save you a month in the laboratory. It's probably even longer than that. So, I mean, some of the ideas, when you learn how to do some of these things, you just go to the library and start looking things up. And there are, I mean, just like when you do Google searches, you don't always find what you want. You find, something that is close to what you want. So someone has done something close to what you want, but then maybe through some thermodynamics, you can kind of figure out what you need to know anyways. So from that, you have to kind of play with the chemical reactions to figure out where you want to go. So, I mean, I know I'm kind of speaking vaguely on this, but that's what you have to do in the real world. Of course, this is academia, right? So, and you're kind of given the puzzles, which are fun. I mean, I think they're fun at least, right? So I'm actually having a good time. So, okay. And the next on the agenda is to have you do one. And like I said, students usually have a hard time with this, so I'd rather dedicate more time to it on Wednesday. So I think I'm going to stop here. But the other point, they have a bunch of tests. I don't know if they're talking about donating them, but there's a bunch of rapid tests that expire today. So if you want to get checked, I'm thinking about going to get checked. It's open today from 4 to 5. So if you're just curious and you have nothing to do, you can go get checked for COVID. It takes 15 minutes. It's not that hard. So if you have nothing else to do, I'm going to be on campus anyways. That's why I'm just going to go down and get checked. So if you're trying to find me in office hours, I disappear for 15 minutes. That's why I'm going to be getting checked for COVID. So anyways, anybody have any questions? No questions. Okay. I'm going to stop recording then.